Alright, class, good afternoon. I've had a couple requests for this problem. It's over the weekend, and we have Thanksgiving break coming up soon, so I figured I'd go ahead and make a video over this. As far as I know, this should be due, I think, the first week of December. But due to the mass majority of the questions I'm getting for this problem, I'm going to go ahead and do a video over it now. So if this benefits you, great. If not, feel free to shoot me a question through email or text message, and we'll get started. So the problem that we're being asked of is problem 8.27 in your book. The problem statement is shown here. The problem asks, the press shown is used to emboss a small seal at E. Knowing that the coefficient of static friction between the vertical guide and the embossing die, D, is 0.30, determine the force exerted by the die on the seal. So, what they are asking us is that this force at 250 newtons at point C is pretty much pushing down, which makes this point D press down on E, which is this seal down here. So they're asking us to find what amount of force D pushes onto force E, given that force 250 newtons. So the challenging part is that the dimensions that they gave us are not perfectly vertical and horizontal. They're at angles. So we're going to have to do some steps to ensure that we get all of our sines and cosines correctly. So we'll go right into the problem statement. So first, we have the drawn figure right here, which is our bell crank with our force BD and the force at DE, D and E. So we need to find the force exerted on the die on the seal with a coefficient of static friction at 0.30. So first, we'll draw the free body diagram. Now the free body diagram, like I said just a minute ago, we're going to have to change our dimensions to make sure we get them in the right spots. So in order to do that, we need to do some trig to get it there. So I'm going to zoom out so we can kind of see the picture while we still get there. So easiest way, we'll just start doing some sine and cosines. So what I'm going to do is I'm going to make the first triangle that you see on the left that has force A, or point A, point B. And then I'm going to go ahead and just label these so we kind of know what we're looking at. This is going to be little a, little b, and little c. We know that little c is 200 millimeters. We know the angle from the horizontal at A to be 60 degrees, and this is 90 degrees. So we need to find the resulting A and B. So we're just going to use some trig. So first, we're going to take our sine of 60 degrees is equal to B over 200 millimeters, which is C. Solving for B, we're going to get 200 millimeters. How about I draw that a little better for y'all? 200 millimeters times our sine at 60 degrees. We get B to be 173.205 millimeters. So if you look back up here, this is our point B, whoops, at 173.205 millimeters. Okay, now we need to find point A. So we're going to use the same thing, but now it's cosine. So cosine of 60 degrees is A over C, which is 200 millimeters. Solving for A, we get 200 millimeters cosine of 60 degrees. We get A to be right at 100 millimeters. So back in our free body diagram, the 100 millimeters will be right there. Alright, so now we need to find points B and C triangle. Alright, so we'll do it again. Drawing our triangle right here. I'm drawing mine nice and clean just to help us out. So now this is point B, that's point C at this 90 degrees. Now we know that this angle is 15 degrees, given to us by the problem statement, or our free body diagram, from right here. So point B is up at an angle from the horizontal at 15 degrees. Alright, so now that we know that, we can do our trig, knowing that I'm going to say this is a, little b, and little c. So again, we know little c, which is our 400 millimeters, is equal to c. Doing our sines and cosines, we get sine of 15 degrees is equal to b over c, which is our 400 millimeters. Solving for b, we get 400 millimeters times the sine of 15 degrees. Little b is equal to 103.53 millimeters. And we're going to do the same thing for little a. So little a is going to be the cosine of 15 degrees is a over c, which is 400 millimeters. So a is 400 millimeters times the cosine of 15 degrees. We get little a to be 386.37 millimeters. Okay, so this guy right here is 386.37 millimeters, and this is 103.53 millimeters. Okay, so now we know all of our dimensions and our perfect vertical and horizontal orientations. Now we can start doing our sum of forces and everything else. So we'll get to that point right now. So we'll take our sum of forces in the x, which is equal to 0, positive in the x direction to the right. We get ax minus force BD. Now force BD, now this perfect triangle that we're normally used to has been flipped to the vertical. So our sine is going to be associated with our x direction, and our cosine is going to be associated with our y direction. So that being said, our force BD is going to be at an angle of sine of 20 degrees, all equal to 0. Two unknowns, we can't do anything to solve, so do our sum of forces in the y, r is equal to 0. We're stating that it's positive in the vertical up direction. We get AY minus 250 newtons plus our force BD cosine of 20 degrees is equal to 0. Now, I know you might be thinking in your head, like, why is in the y direction positive but in the x direction negative? So if you look up from here, let me get my pointer. If you look at point B, force BD in the x direction, which is our horizontal, it's going to the left of B, so that's negative. But if you look at it at B from the vertical direction, it's going still positive up. It's still going up. So that is why in our forces in the y direction, sum of forces, it is y, it is positive, and in our x direction is negative. Okay? So again, we have too many unknowns, so we need to take a moment. So we're going to take a moment about a point that's got the most reactions we can take away from in our problem. So if we look at our free body diagram, our reaction that we need to take a moment about is going to be point A. That'll be the easiest one to take a moment about. So moment about A is equal to 0, assuming counterclockwise positive direction. We get force BD sine of 20 degrees times its perpendicular distance, which is the 173.205 millimeters. So to make sure you understand and know how this force of this moment is going, so this moment is equivalent to our force cross our r. So a basic moment is equal to F cross R, or R cross F. F is just the force. F is right here. That is just the force direction, which is this right here. And our R, which is just our length, this R is just the length, which is this R right here, the 173.205. Okay? So continuing on, all of that is equal to 0. Oh, sorry, never mind. I'm looking at the wrong equation. Now, plus, again, our r cross f, so force BD, woo, cosine of 20 degrees, times its perpendicular distance, which is 100 millimeters, minus our 250 Newton force times its perpendicular distance, which is going to be 100 millimeters plus the 386.37 millimeter distance is all equal to 0. So C, at point C, that 250 newtons, if we're looking at it at pinned at A, this C is going to be a clockwise rotation, so it's going to be negative. But the distance from A to C is this 100 plus the 386 to get to that full distance. Okay? So simplifying out the equation so we can solve, I'm going to pull out our common factor, which is our force BD, times our sine of 20 degrees times the 173.205 millimeters plus cosine of 20 degrees times our 100 plus 386.37 millimeters minus our 250 Newton force times, whoops, I'm sorry, I went ahead of myself. That one is just the 100. Newton force times our 486.37 millimeters is equal to 0. I just went ahead and did that addition. I messed that up beginning, but I corrected it right here. So it's cosine 20 degrees times our 100, and you can see that from up here. Okay. Now, moving everything over and solving for force BD, we get our 250 newtons times our 486.37 millimeters. All of that is going to be over, whoops, pen came off the paper, divided by our sine 20 times 173.205 plus cosine 20 times 100. Okay? So, solving for force BD, we get that to be 793.64 newtons. Okay? So based off a free body diagram that we have just drawn from back up here, it's at that angle of 20 degrees from the vertical. So this force BD is at that angle from our free body diagram. So now we know force BD, but now we need to look at our actual point D on the block that's actually pressing down on the seal. So go ahead and draw ourselves a little block. And I'm drawing mine a little bigger than you don't really have to draw it this big, so I'm just labeling it as D. And I'm going to go ahead and move it down just a little bit so we can have more room to write about. Okay, so our force BD was up and to the left on our main frame. But now we're looking at force D, so this is a force BD was a two-force member. So it now needs to go equal in opposite directions, so it's going to be going down and to the right. Force BD, which is 793.64 newtons, down to the right. And this is at the angle still of 20 degrees. Okay, we're going to have our reaction at D, which is our D is where it's meeting at point E, which is the seal. So our reaction is equal and opposite as well, so it's going to have to be going up. So that is just our force D. We're going to have our friction force. I'm just going to label it as force subscript little f. And then with any amount of friction, we're going to have a normal, which normal is always just perpendicular to the friction force. So I'm going to call this force N. Okay. Now that we have this free body diagram drawn, which is just a free body diagram, now we can do our sum of forces in the x and y again. So our sum of forces in the x are equal to 0, stating positive to the right. So if we look at our force BD, it's going down and to the right, but it's still going positive in the x direction because it's still going to the right. But if you look in the y direction, it's going down. That's what's going to be your negative portion. So you're going to have a positive 793, 0.64 newtons, and that's going to be at that angle sine 20 minus our force neutral or force normal. So Fn is equal to 0. Solving for force Fn, we get 271.4 newtons. This is going to come in handy for us. So when you find any amount of force friction, all it is your coefficient of static friction times the normal force. So our force lowercase f is just our Fn times our mu, which is the 0.3. So we get 271.4 newtons times 0.3. We get friction force, to be 81.43 newtons. Okay, so now this is 81.43 newtons up in the vertical. Okay, so now we can do sum of forces in the y. Sum of forces in the y are equal to 0, positive in the vertical up direction. We have a negative 793.64 newtons cosine of 20 plus our force at D plus our friction force is equal to 0. We know friction force and we can solve for D. So we'll end up having a 793.64 newtons minus our friction force. So we have 793.64 newtons minus 81.43 newtons. We get force D to come out to 664 newtons. Now, from our free body diagram, this was shown as reaction at D to be vertical in the up direction, the vertical up, right? But they asked us in the question to find what force D is doing to point E. So equal and opposite, that force at E is actually going to be going down, or not at, but on E. Okay? And that is all. So in other solutions that you might be able to look up if you don't know how to do it just by yourself, you'll see that some of the solutions they do use the triangle method, the force triangle method, and which you can do if you understand that method. You by all means you can, but it can get kind of confusing, especially when you have like a 3D question or problem you have to do or anything like that. So really doing this method is going to be the normal procedure for future problems, especially when you move on from statics and you go to dynamics, mechanics, machine design, and so on and so forth. So doing this type of formula where you do sum of forces in the x and y and doing a moment, and when you take your moment, instead of doing triangular method, you just look at the components of your design or of your picture, your problem, whatever you're working on, take the component forms, but instead of using like I, J, and K, you just know how the force is crossing to the R, which is your force times your length. The cross, when you looked at a normal moment is equal to R cross F. And that's for component form. Otherwise, the more normal way or the more standard way you can see a moment is just simply the length times the force. And the length is whatever the perpendicular distance is from that force you're looking at. That upside down T is perpendicular. Okay? So, you use the regular R cross F if you have to break it down in component forms, which is I, J, and K. Otherwise, just use the regular, more standard moment equation, which is just your perpendicular length times your force. Okay? So that is the solution for this problem. If you have any questions or you didn't quite follow anything, feel free to pause the video, try to do it yourself, see if what you're getting is what I got. And if you have any other further questions, feel free to shoot me a text or an email, and I'll be glad to help. Other than that, guys, that is it, and I'll catch you all the next time.